So what are neural networks? So let's spend a bit of time thinking about this question. So the modern term for neural network is actually differentiable programming. And we'll see why that is quite soon. And also, just that people know, there's a very nice introduction to neural nets tutorial in the Mathematica documentation. There's a link for that there. And some of it is based on that. Okay, so the very most basic building block of a neural network is a layer. So in other frameworks might call this an operator. So a layer and operator, it's some basic piece of computation that acts on numeric tensors. So let's have a very simple example here. So there's something called element-wise layer, which allows you to have layers for all sorts of element-wise functions like tan h and clip and all kinds of things of that sort. So one thing is, a sort of property of these things is that they can only act on numeric tensors. So here's an example. So element-wise layer, we can apply this to some input. And this is the same as in top level if we said, and they're both the same result. So here's where the differentiable programming idea comes in. So the idea is that you want to have layers that are differentiable. And the reason for that is going to be for being able to optimize and learn what the parameters are in these networks efficiently. So the idea is that if every piece is differentiable, then if you stick them all together, it'll remain differentiable and it'll be very efficient to optimize. So there's a way of differentiating these layers with net port gradient. So you can say, give it some data and you say, I want to get the gradient of the port input. And what is a port? Well, these layers, if you click on it, you can expand it. It says there's a number of ports. So there's an input port and an output port. And the reason for this is that you want some way of being able to specify unambiguously, if you want to connect up, let's say, the output of this thing to something else. In this case, it's trivial. There's just one input and output. But for many layers, they can have multiple inputs or multiple outputs. So you can specify in this case explicitly, like I want the gradient for the input port. So we can do that. And that's exactly equivalent to just differentiating symbolically, and then in this case, just replacing that symbolic variable with some inputs. And what this is really, okay, so there's some other properties that these layers have. So one difference between these layers and other Mathematica functions is that they can operate transparently on GPUs. So it's become imperative to train on GPUs, like CPUs are just too slow. So this can be either CPU or GPU, for example. And you can also, if you have multiple GPUs, you can specify potentially which GPU you want to run this thing on. Like if I had 4 GPUs, then I could do something like that, or 3 GPUs. Okay, so everything works on GPU. So any combination of these things will also work on GPU. Then some other random things. So one is that there's something, this idea of shape inference. So these layers, if you tell it what the input size is going to be, so I'm telling it that in this case it's a matrix of 4 rows and 32 columns, then it will automatically infer what the output shape is going to be. And we'll see a bit later why this is important and useful. Okay, so one of the most important differences, though, between just normal functions in Mathematica and layers is that layers can have learnable parameters. So if this was all that it was doing, so like just, oh, here's another version of tan h or whatever, like there's no way that this thing can learn anything because you just, it's just a function that you're constructing explicitly. But the magic happens when you have learnable parameters. So layers that have learnable parameters, they will often look like this. There'll be something uninitialized. If you click on it, there's the ports, the input and the output. And again, they've got, if I told it what the input was, and I tell it that this thing has, it's a 3-layer net, or sorry, with 3 neurons, let's say, then it knows exactly what the output is going to be. But it also has these parameters here, weights and biases. So these are things that you want to learn, and they can adapt based on the data. So in the beginning, they don't have any values, right? They're not defined. And if you try to extract the values, then it'll just say automatic. But there's a function called NetInitialize, which allows you to initialize these weights and biases to some random values. And that's the general philosophy with neural networks, is that before training, you need to randomly initialize them to something that's not zero, like the weights. If everything is zero, then it has huge difficulties learning. And there's a very complicated procedure for deciding on what the scale of the random data should be that you're initializing these things to. And all of this sort of thing, our framework completely automates. So there's no decisions you need to make. Okay, and then now you can say net extract, and I want to have this dot layer here. I've initialized it, so if I look at the weights, there's actually are some weights now. And I could do the same with biases. Okay, and obviously it goes without saying that I could now evaluate this thing as well. So if, oh, oopsie. So if I was to say .2 of, let's say 1, this thing takes a vector of size 2, it'll now evaluate. But .1, if I try to evaluate this thing on that, it'll say cannot evaluate net because I haven't specified the value for the weights. Okay. So all of these examples so far are things with one input port. So one classic example of something that has multiple input ports is a loss function. So a loss function is something very simple. It basically takes an input and a target, and it tries to have a high number. So it's always a one number loss function, and it tries to have a very low number if the target and the input are very similar, and it has a very high number if they're very far apart. In this case, it's basically the Euclidean distance between two vectors, for example, if these were vectors that I would be putting in. So here's a very simple example. So I have an input and a target, they're quite different. If I make the target, this is 4 and this is 1, if I make this 99, this number goes up. But if I made this 1, this number is now smaller. So this number gives the network an idea of how close it is to the truth. And this is the key part that is used for training the network. There's also, you can list what layers are actually available to you in the system. And each of these obviously has a lot of documentation, and they all have different sort of behavior. So some of them are just, very similar to what Mathematica would do. So things like append layer, it does basically the same thing as append, or like dot plus or dot layer, it does the same thing as Mathematica dot. But then there's a whole bunch of layers that have no analogs in top-level Mathematica. So things like instance normalization layer, which does some sort of normalization of the data, or spatial transformation layer and whatnot. Okay, and this is like becoming proficient in using neural networks involves understanding what all these different layers do and when they're appropriate to use. And that's going to be probably a larger topic that will be carried on for the next, I think, sessions. Okay, so at least one of them, what does the linear layer do at least? So this is the simplest learnable layer. And this is sort of also one of the oldest layer types. And I must mention that these layers, they keep growing. One of the reasons is that people invent new layers all the time. And as they invent them, we want to implement them and have them in our framework. Okay, so the simplest learnable layer is just the linear layer. So the Mathematica equivalent of that will be this. You just dot producting the weight and the data, and then you're adding some bias term. So the data is some sort of vector, and the weight is a matrix. So basically what this layer is doing, and we can just verify that it is actually the same. We can extract the actual weights. Oh dear, what's going on there? Oh, I didn't, sorry. Initialize that, there we go. Okay, so all that this is doing, like the linear layer, it's often called a fully connected layer because you could interpret, there's let's say an input vector of length 3, so 1, 2, 3. So this is what this input here might look like, and there's basically the matrix can be that you've got the weight matrix can be interpreted as sort of connections between this neuron and the neurons of the output. and there's a weight per connection. So that weight matrix basically represents that. And all that it is a linear transformation of the data. And linear transformations, they can have things like they can rotate the vector, they can rescale it, they can shift it a bit, etc., etc. So whatever linear transformation can do, this layer can learn to do that thing if it's good for producing the predicted result. Okay, but this is a big topic, and things like what do convolution layers do and what do pooling layers do, etc., etc., or recurrent layers, these are going to be topics that will be very deeply explored, I think, in the next talks. So I'm not going to go into that too much. Okay, so layers, I think we've understood now, right? So layers, they act on numeric tensors, and they have a whole bunch of properties, like they're differentiable, and they work on all different devices, etc., etc. But layers themselves are not very useful. Like, just that linear layer, it can't really learn much. And in fact, one linear layer is the same as logistic regression if you were to do a classification problem and try and solve it with a single hidden layer network. Or linear regression as if you try and, if you're predicting a numerical value with a single linear layer. So, and those are very weak sort of learning systems. So one of the main ideas of neural networks, or deep learning, I guess, is that you want to have a long set of transformations, a deep set of transformations that allow much more complicated behavior to be learned than just single layers. So the first container type is a chain. So this is very simple. So a chain is simply a linear, it's a sequence of operations. So a linear sequence. So it has one input. We can try this out. So if we look at this thing here, so this thing has one input, it has one output, and it just is doing first the 10H, and then it's doing the logistic sigmoid on the data. And this is exactly the same as this, for example, in top level. And you can also verify that they're the same. Okay, this is a bit of a silly example because you could, in this case, it would also be equivalent. So element-wise layer is a very powerful layer. It can have, for example, something like this. So logistic sigmoid takes in that, and that takes in, and that's a perfectly valid layer. You can compose all the different primitives that an element-wise layer has, and you can make a pure function, and that's a perfectly valid element-wise layer. So this will be the better way of writing this thing. But this is just to show that what this actually does. Okay, so a lot of networks, and traditionally almost all the networks have been just chains. So yeah, the sort of traditional image classification networks, even the one that won ImageNet, they can all be represented by this chain construct. That's all they need. However, what happened after the 2012 ImageNet result was that people realized that there's a lot of power in having actual or more complicated sort of structures that you can have. And one of them is the graph. So a very simple graph would be something like this. You have two different inputs, and these inputs, this first input goes into tan H, the second one goes into logistic sigmoid, and then they get added up together and then returned. So this graph, the idea is that you can, the first sort of list here, and this can be a list or an association. So if it's a list, it means you basically, you have all the layers that you want. And then the second argument for netgraph is a list that gives the connectivity structure. So just exactly like graph, how graph works. So in this case, I'm saying that the first port of the input is going to the first layer, so tan H, and the second port of the input goes to the second element in here, this one here. And then both of these go to the total layer, which totals them up. And you can do the same thing with association and then with names rather. Some people find that much easier. So tan H goes to that, and then you'd have this stuff here, for example, changing to being tan H. I personally prefer that method as well. And this must obviously be an association. And these ones must be changed to do. Okay, so the question then is, is this equivalent? What is this equivalent to? And in this case, it's just function composition like this. Okay, so you can build very complicated structures with NetGraph. You can also differentiate it, because all the layers are differentiable, so will the NetGraph be differentiable. And this is an important point, is that containers behave exactly like just normal layers. So they're differentiable, they're on the GPUs, but they can also be nested. So NetChain expects a layer over here, but a NetChain is a layer as well. So this is perfectly valid syntax. And if you dig deep into this thing, you can find the different layers of NetChain, sorry. Okay, and obviously the models in the repository are almost all some form of container. So an example of this would be this restyling net. This thing has two different inputs, the style image and the content image, and it does some processing. And you can dig deeper and click on these things and get, see what it looks like. Okay. So containers are important for building more complicated structures. But containers and layers, they still only ever operate on numerical tensors. But what we had, what you might have noticed right in the beginning, was acting on actual images. Like we would take a net model, this thing, and it would apply directly to the image. So how does that, how does that happen? So the basic idea is that we have another construct, and this construct is quite different from anything that we've seen in other frameworks. So the construct is the idea of a NetEncoder. So NetEncoders are special, almost like a layer, but they can't go inside the net graph or net chain, or they're not real there. They're not differentiable. They don't work on all the devices, etc., etc. But they can be attached to the inputs of other layers, which we'll see now. So basically, what they do is they take some type, so like an image or an audio object or text, or any of the other types that you might want to operate on with neural networks, and it basically produces the appropriate tensor from that thing. And you can see from this, so this says, okay, it must be a grayscale image. It has one color channel. There's no mean or variance images that you could set as well. And it's got an output shape of this. So if you give it an image, it produces this tensor. So it makes a guarantee that the tensor that this thing outputs is a 1 by 12 by 12 tensor. And if this image was much bigger, it would just reshape it. If it was a different color space, it would conform it. So it can basically guarantee to the network, this is the kind of tensor that you'll be getting. And another cool thing that you can do with this sort of thing, with an encoder, is that it can operate directly on files as well. So if I have a file for some image, then it can directly run this and give you the tensor. And this should be 1 by 12 by 12. Oopsie, sorry. 1 by 12 by 12. Great. And the reason why this is powerful is that you can do out-of-core learning for images and audio files with this, because you just have to, you can use the file as an actual data point to feed to the training, for example. So you don't actually have to load all the files into memory. You can just have them on disk and then just give the file names, and then NetTrain can act directly on them, or the networks can act directly on just the file paths. So file paths are completely valid inputs to these encoders. And if you're more interested in, I was going to touch more on this later, but I decided to simplify things. So if you are interested in training on large data sets, then there's a tutorial on doing this. Okay, which I recommend you looking. And so there's a whole bunch of other encoders, from audio to characters to for tokens to, you can write your own custom encoder as well. So it depends on what data type that you're dealing with. Okay, and as I mentioned, the main sort of property of these things is that, remember the input port, So you can specify what the size is for the input port, but instead of doing that, you can attach an encoder to it. And if I do that, instead of saying what the size is, it will tell you that the input is an image in this case. And what this means is that you can act directly. So this case is a pooling layer. You can act directly on an image. If you try to do that without this, it'll just complain because it's not a type that it accepts. So if we did this pooling layer and we said, let's give it some image, data supplied to port input was not a tensor of rank greater than 1. Okay, and one more thing. If you remember the networks that we showed right in the beginning, for ImageNet, these things had the magical property that here's the net chain. They could be directly applied to the image. Just give it to the, give the image to the network. And the reason for that is that it has this image encoder on top. And you can always extract the image encoder. You can say net extract of the input, and you can see what this image encoder is doing. It's resizing them to 299 by 299. It has some mean images, it's a mean image. It has, and it's RGB color space. So that's why this network just works out of the box. So for other frameworks, you often have extra pre-processing code that would have to conform the image into the size that the network requires. Okay. The basic, almost brother of the analog of the net encoder is for the input is that there's going to be a net decoder for the output. And the reason for this is very simple. It's that for a lot of networks, for example, like classification tasks, you really want, the network is always going to give you back a numeric tensor, but that's not really what you want. You want some sort of class. You want to say, is this a dog or a cat, for example? So what this does is that if you create this decoder, you say it's a class decoder, and there's two classes, there's a dog and a cat. If I give it a probability vector, it will then interpret, it'll take the maximum probability, which is 0.9, and say this was a cat, because that's the one that corresponds to 0.9. And you can use this exactly like a classify function, which is that you can ask for different properties here, like what are the probabilities? And it'll give you an association with the probabilities for each of the things. And exactly the same analog, if you have you can attach this to the output port of a network. And this is, you can see now why these ports also need names. Like you need ways of referring to them. So like if there were multiple outputs for something, how do I specify which output to attach some decoder to, for example? Okay, in this case, there's a softmax layer, which basically just it takes a random vector and it produces a normalized vector, so that sums to 1. If we apply this, now softmax directly works on, it directly produces something like this, which is definitely not just a numeric array. Okay. So the same thing happens with these networks. So things like this ImageNet network, it has a whole bunch of classes, and if you click on this thing, you'll see that the output has a class attached to it, which we could extract. And if we run this network, it means instead of giving you, just a big splurge of probabilities, like there's a vector of size 1001 in this case, you can actually get the real class from that. And you can, obviously, if you want the probabilities, you can ask for them here as well, but this might take some time. Okay, and you can get the output decoder in this case, and you can get the class labels and all that sort of thing out if you really want. Okay, so I hope that people can see sort of what the motivation of this thing is, that it makes the networks very clean. Like this is ready to go, this network. It doesn't require lots of post-processing scripts and whatnot. So, okay, so now that we've discussed the main sort of concepts, so there was decoders, encoders, containers, and layers. So now we actually want to train something. So that these networks are not very interesting unless you can actually do some, that it can do some learning. So how do we do this? Well, there's a whole bunch of automation that's introduced by the framework, but I'm going to show you some examples where I don't make use of this automation and just do it very explicitly that you can see exactly what's going on. So here's a very simple example. We have some data, which is pretty much a straight line. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. And here's a very simple net that we want to have to solve this problem. So in this case, we're predicting one number, a vector of size 1. And here's where the magic happens. So we have an input. It comes in, it goes through the linear layer, and this has parameters. And we want to find the parameters so that the prediction of this linear layer is the same as the target prediction, so that the mean squared loss layer becomes very small. So if we do it right now, we've initialized this network. It's just random initialization. This is pretty big. So obviously that's what we expect, because these parameters haven't seen any of the data. They're just randomly picked. So currently the predictions of the network of this linear layer don't match at all what the target looks like. Okay, so now we can actually train it. And there's a very simple construct called nettrain. So nettrain takes a network, and it takes some data, the training data, and it will train. So that happened very quickly. We can do it again. So basically, this tells you here what the output looks like as a function of training iterations. So it does many iterations, and you hope that thing goes down, because you want the loss to get smaller, which means that your predictions and your target match. And now we can check exactly the same thing, which previously we had 15.31. If we run this now with a trained network, we get something like that. So this network now has learned to predict what the target looks like. Okay, and we can also extract the parameters. We had a net with some weights, and we have a new network, the trained network. And we can see what the weights look like. So for the trained net, the weights are completely different. And that's the whole point of training, that it can change the parameters. Okay, and just a quick rough idea of how this works. It uses something called gradient descent. And this is where the differentiability comes in and where it's so important. So the basic idea is, suppose this J here is the loss. So it's a function of the weights of the network, right? Or the parameters of the network. So we want to find, so for different parameters that you have, this loss is going to be different values. And as we saw, so there's going to be a point, though, where there's going to be a minimum. And in fact, there's multiple minimas. So there's a whole landscape of minima. But the basic idea is that if you're a blob and if you're sitting over here in parameter space, so if your parameter puts you on over here, then if you have the gradient gives you an idea of the direction that you must go so that you get more closer to the minimum. And that's what nettrain basically does. It uses the differentiability of the net, and it moves you in the direction where you need to go. Okay, so this is also very similar, people might realize, to things like n-minimize or find minima, except that it's vastly more efficient for various reasons. Okay, so that's the basic idea of the training, and you don't have to worry it's good to know what it's doing, but nettrain does automate a lot of that stuff for you. So now that we have this background, let us actually look at a real sort of example. And this is often considered a toy example, but it is the simplest toy, maybe the least trivial toy example that you can have that actually does something nice. So we get the data, and we can look at some examples, and probably most of you have seen this sort of thing. And one of the reasons for using this example as a starting point is that a lot of people have seen it, and it's familiar, the problem that is involved with this. So the problem is very simple. You have some handwritten digits, and you have the actual label. And so you want to predict for unseen images. You want to learn how to predict the correct label for those. So what have we learned? Well, the first thing, obviously, and this is something that I think that the next speakers will emphasize a lot, but basically, it's very seldom where you will be actually putting together very complicated nets from scratch with lots and lots of layers. So the most common thing is, the neural network community has spent a lot of money and time looking for good architectures for doing certain problems. So your first instinct should always be to say, let's go to the neural network repository and find something that does something similar to what we're doing. If it's image classification, there's a whole bunch of incredible networks that have won on ImageNet that will be a very good fit for what you're doing. And it's unlikely that you'll ever find a better architecture. So this should be your first instinct, almost always. Find an existing network for a certain task. And one other reason why it's very nice to use the repository is that you are guaranteed that the implementation was correct. It's very easy to see a paper and then make mistakes with these numbers. Like, this is a very small net. You're probably not going to make mistakes. But for some of the networks that have 500 or 1,000 layers, it's very easy to make small mistakes, and then the whole network doesn't work properly. So yeah, so this should be your first instinct. And in fact, for this particular task, there's a very famous network that we have called LeNet, which at some point supposedly sorted about 10% of America's checks. This was like in the early 90s. Jan LeCun worked for, I think, Bell Labs, and they made one of the first sort of industrial grade neural network recognition machines for check digit recognition. So it has a very pristine history, or prestigious history. So this network does exactly what we want. It's a very simple network. It has convolution layers and pooling, and this is something that for the image talk, I'm pretty sure they'll explain carefully what these layers do and why they're special and why they're used for images. But yeah, so you could run this model immediately and you'll see that it works. But let's do this from scratch. So using all the different things we learned. And I also want to say, if you want to see the most efficient way, or the fastest way of doing this sort of task, there's a tutorial for MNIST digit classification, and it's very, very short. It's a very, very simple few lines of code to actually do this the simplest way. But the simplest way is not the most general way. So the simplest way works for problems where there's basically one prediction, where there's one input, but it doesn't work for anything else. So we're going to show for this basically the general approach that'll work for any sort of problem, even though it makes, for this very, very simple problem, it makes it look a lot harder than it is. Okay, so the first thing that we want is we want a decoder, because we want this thing to predict the classes, and the classes are going to be between 0 and 9, because the digits are between that. And we also want an encoder, which takes an image, and it makes sure that it's 28 by 28, the size, and they're going to be grayscale. Okay, so the next thing is to actually define this convolutional network. So I'm not going to explain all that carefully about what the motivation is for each of these things. Maybe the only thing I'll mention is that convolutions are usually used for structures like sound, like spectrograms or images, which are large, and you don't want blow up of your parameters. Like the fully connected layer or the linear layer gets incredibly large for images. Like if you have a 500 by 500 image and then you need a matrix that multiplies that, you just have a blow up of parameters. But there's a whole bunch of other reasons. Like there's certain symmetries that are encoded or invariances that you hard code into this here. So you say things like, for a classification problem, I don't care that the object could be anywhere in the image. I don't really care. And that's invariance to shifting the object in the image. That's one of the reasons why you have a pooling layer, for example. So you can prove that a pooling layer makes it equivariant to translations, or an object to translations in the image. And so this is sort of principle in neural networks, is that if you can encode structure, so if you know that there's some structure in your input, you want to use layers appropriate for that to exploit that structure, and it makes learning a lot more efficient. But this is a longer topic that maybe we can deal with some other time on the next version, or maybe even the questions. Okay, but basically, yeah, so there's a whole bunch of convolution layers. There's a nonlinearity called like a ramp layer. And this is a very important thing probably to know as well. So if you plotted this thing, it'll just look like, let's say, -3 to 3. And this thing it's flat, and then it goes upwards like this. This is also called ReLU layer sometimes, or rectified linear layer. And you'll see them between things like linear layers or convolutions or whatever. And they basically break the sort of linearity. Each of these operations is a linear operation. And so you have a bit of nonlinear behavior here, and that helps the network learn much better. Okay, so we've now created this thing. Now, this is where things become more complicated than they need to be for this very simple example. But I'm going to show how to do this for the general case. So here I'm actually constructing the training net. So for these simple examples, you can actually feed this straight into NetTrain, and it'll construct the whole learning graph or the training net itself, and then give you back the original network that you had. But that doesn't work for all networks, especially when there's multiple inputs or outputs. So what you can do is, in this case, here's the net, which is having the uninitialized net. So the input goes to that. And then the input goes to loss, which we've just explicitly added here. And this will be cross-entropy loss layer. And cross-entropy loss is usually what you use for classification. So this is one of the things that you have to learn as well, like what losses are appropriate for different tasks. And this is a very good loss if you have two different probability distributions that you're comparing. Okay. And we can evaluate this in some training examples, and you'll see that it's quite large. Okay, so we have this training net, and we want to find the parameters in the net so that the prediction that it makes is similar to what the target is, and the loss gives you a number that will be small when that happens. There's one more thing, which is that this net now has two ports. It has a target port and an input port. So the most general way of representing data when there are multiple ports is the association form. So basically you have this sort of thing. So you have one port and it has a bunch of examples, and then there's another port that has a bunch of examples. So for training, this is the most general form. And some networks, they might have 5 of these ports, and so you can easily represent that data. Okay. Now let's train this thing. So this is a more complicated syntax of the previous thing that I had, but let's start this. So the first thing to note is that I'm going to use GPU. Now, not everyone can use GPU. You can only use it if you have an NVIDIA graphics card, unfortunately. So whilst it's running, we can explain what all the different things are. And sorry, also this display looks a bit strange for presentations. There's some bug. It makes it look small. Okay, so it's busy training. So let's look at all the different pieces whilst it's doing that. So there's the training net, there's the training data association, there's a validation set. Now this is very important. So when you use things like Classifier, there's a lot of things that are automated for you to prevent things like overfitting. So overfitting means that you do very well in your training data, but you do terribly on any other data. And there's a very good tutorial on overfitting if you're really interested in that. Called tutorial, training your networks with rigorization. So basically this validation set, what it does, it's not allowed to use this data for training, but it checks, as you can see here. So this loss curve, the blue is the validation performance. And as you can see, it's getting better and better on the training set, but it's not getting better on the validation set. So what this will do is it'll say, okay, we can take the network that did the best on the validation set and return that to the user. So for example, this graph might look like, the validation set goes down, 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 and then suddenly it can go up again. And that's the sort of classic signature of overfitting. So in this case, it doesn't look like it's overfitted too much. It looks quite fine. But this thing, if you provided a validation set, it'll protect you quite well from any sort of overfitting, because it'll just take the point that it did the best on the validation set on, where it wasn't overfitting yet. And that's really probably the most recommended thing for people to do to save themselves from that problem. Because yeah, like NetTrain doesn't automatically, deal with overfitting like Classifier and Predict might do. Okay, a whole bunch, some other things, like how many rounds of training. This means how many times does it go through the entire data set before it stops. And you can obviously, we can actually run this one more time. You can stop the training at any point. So if I wanted to stop it now, I could just say stop and it will return the training result for me. Okay, that was maybe not the greatest idea because I have to retrain it for a little bit at least. And yes, and this last thing was that there's an argument all here. It just means that it returns this nettrain results object. So normally if you don't give this argument, it will return the actual train network. But in this case, it gives back the train network that's in this object, but it gives back all the other training information as well. So things like what was the validation loss, et cetera, et cetera. And we'll see that now. So this is almost done. And this will take a lot longer on your CPU, unfortunately. Okay, let's stop it now. Okay, so we have this network that's been trained with the result object. So from the result object, there's a whole bunch of properties that you have. So things like you can get a nice plot of the, of the loss for training, for the training set, which is the orange, and also the blue, which is the validation set loss. And we can see that it hasn't overfitted too much because the validation set is still going down. Okay, we can also get the network out. So results train net will give you back the net graph. So what we really want though is we want the prediction network. So we want to get out, this net graph, but also inside the net graph, there's a node LiNet, which is the prediction graph. We can discard the rest of the network because we're not doing training anymore. So there's a little bit of annoyance that you have to do, which is that the encoders disappear if you, this thing is now, if you extract this thing, the output encoder is not there and the input encoder is not there. So you have to just put them back, which is pretty simple with net replace part. And we can now use this train net to actually make some predictions. So this is a 2, and we can get some probabilities out. It's pretty confident that this is a 3, but it's a bit unsure. And as you can see, like it's been cut out a bit. So that's pretty good that it's not 100% confident. And you can do things like obtain the accuracy of this thing, which gets about 98.6. So that's roughly, So for classification tasks, it's very simple to get metrics out because you can just use classifier measurements. So if it's a classification task, there's classifier measurements, and the same thing that happens with predictor if you're doing regression. Okay, and this is a duplicate. Oopsie. You can do the same thing with classify as well. So you can try run classify. And you can see how much simpler classify is than this. So classify is fully automated. It does all the pre-processing. It does everything for you basically. And all of this rigmarole that we went through, you can achieve something similar with classify, except that classify has a lot of limitations. It's not as flexible. You can't do out-of-core learning, et cetera, et cetera. And obviously, if the only problem was to do simple image classification, then something like classify might be appropriate. Okay, let's just stop it. I don't have that much time. Okay, well, we didn't let it train very long, but got that. Okay, so just to summarize quickly. So I've given a very basic introduction to the framework and different pieces of it. And there's obviously, I gave lots of links to things that are more complicated. So things like out-of-core training, there's all kinds of other ways of dealing with overfitting. So things like using dropout or other kinds of regularization. So those are things that you probably have to look at yourself. Just a quick sort of rundown of this framework. So first of all, it's an industrial strength scalable framework. We use all the latest NVIDIA libraries. We use MXNet as a backend, and we contribute to MXNet as well. So all the companies that are working on MXNet, and it's backed by a whole bunch of companies, from Amazon to Apple to others. Users automatically get all the benefits that accrue to all the things that improvements are made to MXNet. We also use this extensively in Wolfram Research, and we also plan to have the best repository of networks, which is already, I think, a lot better than any other frameworks repository. So we're putting a lot of effort into collecting from nets from other frameworks. So we convert them for you. We convert the pre-processing into Mathematica codes if there's pre-processing involved, and all the hassle of converting. And converting is a tricky business. So yes, and also the networks that we train ourselves are going to go into this repository. There's no lock-in. So we thought it was a very important principle to follow, that users of the framework are not forced to have their stuff only in Mathematica. And we've tried to make ourselves be easier to use than other frameworks. And also one thing I didn't mention was that we do support quite simple cloud deployment. So like API function and cloud deploy that allow you to deploy these networks onto the Wolfram cloud for you to make APIs with.